Good morning, everybody, and welcome to our next day of the Passive House Designer course. So was it a lot what we covered already, guys? Yeah? Did you learn? Did you know more today than you know a week ago? Yeah, guys, and it's sometimes difficult to see that in position that you are in. Think about just over a year ago. The only way of doing the designer course was traveling to Melbourne or to Sydney, sitting there for 2 weeks straight. Yeah, and then after the last day of course, you're writing the exam. So if you think about it, and there has been no formula sheet like Julia just showed you, like that formula sheet has not been existing. The homework and exercises that you're getting, they have not been existing. We're using old exam questions from the 90s where German English is really confusing in there, and it's not developing with the course itself. So you were doing already vapor calculations and really crazy stuff on the first day, and you have never heard of it. And there's never been recordings really. Yeah, so now you even have the recordings of the units, like the actual teaching. Before we were not allowed to share the recordings because the Passive House Institute had us signing a paper that we are not allowed to share recordings of their material. Like we have students that say, we would like to go through this material faster. But guys, for the ones that might be even in this class, if you want to go through this material faster than we're going already, we're losing a lot of other people on the other hand. Yeah, so this is now the middle ground that we found. The material is a lot, it's complex, and especially the opaque building envelope data we had it's a lot of content because we speak about 3 passive house principles. We speak about the thermal insulation, the thermal bridge-free design, and we speak about the airtightness. Yeah, and all that stuff from where it comes from is like in Europe, airtightness, thermal bridge-free design, and U-value calculations, all that stuff is done. Like I've done all that stuff in my carpenter careers in 1999 already. Like my first year of apprenticeship, I've done all these calculations. So for me, it's not so much new. And as well, for a lot of Europeans, it's not new. They had that in their teachings. But for you guys, it's often completely new. You have never really looked at N50 values, like an air exchange rate of 0.6 at a pressure difference at 50 pascals. It's challenging this day because it's such a complex construct, and it's the first really heavy day on being back in the classroom. Like a lot of you guys, you're business owners, you're team leaders, and you're normally giving directions and you don't have to listen so much. Then actually listening to Julia and myself for 8 hours a day straight, talking about completely new concepts. And maybe that helps you to appreciate your apprentices, your people that you're training, how hard it is actually to learn new things. Yeah, so that might be something to put out there as well a bit. You have now the opportunity to review this material. Like we had this meeting with our beta testers and they say it's so much easier, this content now, than it has been before. However, I think it's a bit unfair. They've done the course before. Obviously, it's easier. They heard it before. They obviously have done it, and it obviously clicks easier, the material. But we took so much clutter out of the course that I think is not really helpful or needed. And we're bringing it down to the far more basics and fundamentals. And we keep repeating them. You probably have seen there's been a lot of repetition as well. I'm normally flying over some slides really quickly at the beginning so that you have seen them. And then when they come later in the presentations, then I go into them a little bit deeper again. And then I'm going deeper again, until we've covered everything. I'm trying to do is I'm trying to give you the visual of it, that you've seen it and you say, okay, I've seen it before. And then we're going deeper into the material in the later stage, because if I give you all the little details and nitty-gritty things on the comfort zone, on vapor transport, on all that things at the point where you hear it the first time, I think it would be like even more overwhelming like it is right now. So trust us. believe us, we've spent a lot of time on thinking and putting that together to making this experience as good as possible for you. We're having a pass rate over 99%. We know what we're doing. Let us take you on the hand on this journey, and we get through this. Yeah, so that will be all good. So, and then as well, you may have realized we're taking a lot of time in our homework and exercises. I don't know if you noticed. The reason is this is the time where you actually physically do something, and I think there's the learning process is the highest, and now things start to come together, and that's where you can ask questions. And as well, you probably appreciate Julia's pace in there. Like, imagine me going through that. It would be probably a bit crazier. So that's the reason why Julia is doing homework and exercises, and I'm more doing the bigger contents. It's a personality thing. Yeah, like I'm this hyper crazy guy. Yeah, that has a brain thinking super fast, and I've been spending the last few months in my little box and putting this material together, and I'm out there and have to bring now my thinking speed of a communication speed again. So if I'm going sometimes a bit too fast, I'm sorry. Say, Daniel, slow down, and then I probably can go down that. On this note, warning, today we may go over time. And the reason is we're speaking about the most important part of the building envelope. The thing that is most of the times goes wrong, that is the most expensive part of it. The only thing that connects us between the inside and the outside, it's so misunderstood, windows. Yeah, and as well, what we're doing at the end of the day, and that's that special presentation, I think that's the cherry of on the cake, is this wall, roof, ground presentation, where we talk about the joining of the different parts, because this is the thing that's going wrong. Like, designing a wall build-up is easy, designing a roof build-up is easy, but how to join these things together in a way that it actually works, that's the difficult part. And that's the reason I want to spend a bit more time on that. And we may run a little bit late today with the exercises. If you have things in the night that you have to attend, keep in mind you can go through the recordings of the exercises. Yeah, like we have that all as recordings, and you can go through that material later. Just to let you know, I want to warn you as well, back when we were still teaching face-to-face, one-on-one, we often went to 6:30 in the class. Yeah, like because I was alone in the classroom, I was talking with them, and I didn't watch my clock the whole time. And then you just get lost. Like, we could spend easily twice as much time on every single slide set, but we have to be careful with the timing as well. So sometimes I push it a bit faster so we get through the material. What did we learn to now? So the first day that we had now, like the core content, that was our opaque building envelope. And like I said, we covered 3 of the Passive House components, the 3 Passive House principles: this thermal insulation, the thermal bridge-free design, and airtightness. And as well, it's the first time that we're going into this material. And as well, we really stress the difference between air tightness and vapor tightness. So we're having an air barrier system and a vapor control or vapor barrier system. And we really try to stress that, what is often not stressed, and people often mix these things up. So that's the reason we spent actually a lot of time on that. The first thing we learned on Tuesday last week was the U-value concept. You learned how the U-value concept works. All comes down to the material's thermal conductivity and the thickness of the material. That's all what you need to know for that concept. And that is giving us 80% of the results of the thermal envelope. 80% of the results is done by the U-value concept. Additional to that, we're having the thermal capacity, the thermal mass, C, that we haven't even talked about yet. We'll cover that on our heating and cooling day, how that comes in. And the only thing that thermal capacity is doing is helping us with the thermal lag time and making that energy transport slower. So that when the sun hits the surface, the heat is not coming through half an hour later. What could happen in a 90 millimeter cheap fiberglass insulation and thin plasterboard buildup that an hour later, the heat is already on the other side. Yeah, so the thermal capacity, so the thermal mass helps us with slowing down that heat wave through the structure. And then the other thing that is really, really important is the airtightness. The U-value concept is based on 100% airtight structure. And as less airtight the structure is, as less we can tell the actual performance of the building. So only airtight buildings, we can get a really close calculation that is realistic to the physical world. Soon we are having a building that is really leaky. We have no idea what type of air leakage we have. So that was the airtightness part. Do we have an energy leak that lets a lot of energy through? Or do we having a moisture leak that it's probably less air moving through, but because of the time spending in the structure, we have now condensation in our structure, and now this condensation is causing a durability issue. Yeah, so the energy leak is just a sustainability and energy efficiency issue, but the moisture leak that is causing condensation in our structure is actually a health risk, a hygiene issue, and a durability issue. So that's the thing that we spoke about. And we know that we're not building 100% airtight. We know that the Passive House Institute says 0.6 air exchanges are okay. We don't need to go tighter than that. If you're achieving this, we are happy with it. The calculation results are close enough, and we're not causing too many condensation issues or mold issues in the structure. And Julia said that as well. She asked, where's the 0.6 coming from? And they told her, we don't know. Like, it's something that we believe that the industry is able to deliver. In Europe, a lot of my friends, they have now 0.2, 0.3, sometimes below 0.2 air exchanges as their normal results, because the building industry is already more prepared. Here in Australia, 0.6 is amazing. Yeah, like if you're achieving 0.6, and a year ago, I nearly saw no 0.6 measurements coming up in social media and stuff like this. Now, more or less every week, somebody else shows their results online and say, yeah, another 0.3, 0.2. Sometimes I can't believe the numbers. So I'm not sometimes skeptical, because I'm not sure if they did the volume calculation correct, like from finish to finish, like we discussed that in the airtightness part, that they actually went into the plan and took the volume from the plan. What is a different volume that is physically there? It's still an amazing performance, yeah. But the volume calculation is a tricky one on the Passive House side, because it's a part of the certification process. So we have to be careful of how we actually measure that, and what we're presenting to the certifier, that we know that is done as the standard is asking it. Then we learned that we have to stop the warm air to get cold. And to do that, we have to put a physical barrier between the warm air and the cold surface. Yeah, so we have to make sure that warm air never gets so cold that we're having our condensation issues. And for this, we're putting our air tightness system in place. And it has to be on the warm side of the thermal insulation. Yeah, so why does it need to be on the warm side of the thermal insulation? Because we want to stop the warm air moving through the thermal insulation, dropping in temperature, and then coming to the 80% relative humidity, where we have mold growth, a hygiene issue, or it comes even to the 100% relative humidity. That means condensation, a durability issue. So that was the next thing that we really focused on. We learned that air needs a physical hole to move. Yeah, it needs a physical hole to move from A to B. Yeah, like a sponge has physical holes. You see them, and there the air can move through. It doesn't go through material itself. It needs a physical hole. Sometimes it's in a nearly micro level, but it needs a physical hole to move from A to B. Yeah, this is and as well, the air tightness works with pressure differences. Yeah, so it finds its way. And the difference between water and air is that water has a two-dimensional, like when we speak about rain also, has a two-dimensional approach. So if you overlap from the outside to the inside, then the water runs down. It comes not up behind the membrane. However, with air movement, soon there's a pressure difference between inside and outside. The hole is there. The air finds its way. It always finds its way. So we really need to tape these joints. And then we learned that because the air tightness system needs to be on the warm side of the thermal insulation. When the temperature is lower than 20 degrees, we want to have it inside of the building. When the temperature is higher than 25 degrees, we want to have it outside of the building. Obviously, we're not always having that situation. Like we're having temperatures that are going from 0 degrees up to 45 degrees in Sydney, for example. So there's a time of the year where we rather have it inside, and we have a time of the year where we have it rather outside. Usually we rather have it internally. The reason for that is really simple. Everything that happens behind the air tightness membrane is having a small impact on the indoor air quality. So if we would have a mold grow in our structure, and our air tightness is now a barrier between that mold growth and our indoor condition, then at least from a health perspective, this is not having an impact. If we're using building materials that are off-gassing, we have like treated timber for termites. Like, I don't know if that is harmful for humans or not. Like, they tell us it's not. But we have paints, external paints that you can't use internal. That could come in. We have different stuff in the structure. And if we are having our air tightness system between that material or that moisture issue we're having, then at least from a health perspective, we are more protected. That's the reason I'm always trying to stay with the air tightness system on the inside of the structure, if possible, to make sure we're having a better air quality. However, there are as well situations where we need to move it outside, for example, Darwin or so, where the temperatures are rather on the high side. When that happens, is not so easy and so clear. For this, we rather do a WUFI calculation. Then, after we went all this air tightness and thermal insulation, we went into the wall, roof, ground buildups, and realized that the buildups are actually not really difficult. Like the only difference between a mild climate and a really harsh climate at the end is the thickness of insulation. Yeah, so we don't really need to change our buildups, our structure. We only have to think about how we increase the thickness of our insulation. We probably need a thicker screw to fix external finishes because it has a higher counterlever going through the thermal insulation. But at the end, there is not a big difference between the different climates. Doesn't matter what building material we use. If you're using brick, CLT, concrete, it's just a thermal insulation layer external stick to it. If you're using a timber frame, we can use the timber frame as our thermal insulation layer. But when that is not economical any longer, then we do the same. We put thermal insulation externally. Happy days. Yeah, so there is not a big difference. The same would be with straw bales, SIPs, ICF, or whatever types of insulation you're using. You just have to increase the thickness of insulation. The only thing we have to really be careful is where do we put our air tightness system and our vapor control system. And for this, we normally do a WUFI calculation. And in the cold climate, we have to be careful with the external finish. In other words, polymer render or metal sheeting directly on our thermal insulation without a ventilation. This could cause condensation issues because it's not vapor open, and now the vapor is trapped in our structure. And in a hot climate, we have to be careful with the internal finish, like tiles, vinyl sheeting, mirrors, glazing. I'm not speaking of the window glazing, but sometimes people have a glazing on the wall, or like a mirror on the wall, like a flashback behind the cooker. Can't remember, like that glazing that people put in. We have to be careful with these things if they actually work in a hot climate. Cold climate, no problem, because it's a vapor barrier or like an air barrier, vapor barrier internally, no problem. But in a hot climate, we have to be careful with the internal finishes. In a cold climate, we have to be more careful with the external finishes like polymer render or metal sheeting directly of on our thermal insulation layer. Something that nobody talks about, but needs to be understood. And then we spoke about the thermal bridges. We realized that the buildups are not difficult, but joining the buildups is difficult because every change of direction or change of material is causing a thermal bridge. Every change of direction or change of material is causing a thermal bridge. And we know there's only two types of thermal bridges: point thermal bridges and linear thermal bridges. So this causes of change of direction and change of material are causing the thermal bridges called point thermal bridge and linear thermal bridge. Point thermal bridge is just a penetration, could be a pillar, not a pillow, I guess. We don't have so many pillows. Maybe we should have a few pillows in our walls, but for thermal insulation reasons, they're not causing too much thermal bridging, but like a pipe or a pillar or like a steel beam or something like that, it's a point thermal bridge. Or we could have a linear thermal bridge, like an external corner, a wall roof junction, or concrete slab on ground to wall. These are all thermal bridges. The question is, when do we have to address a thermal bridge? And that's the significance. Like when is the thermal bridge significant enough to be added to our calculation? We don't have to add every staple. We don't have to add every screw. We don't have to add every plasterboard joint or something like that. That they're all causing thermal bridges, but they're not significant enough to actually be entered into the PHBP. And the Passive House Institute says there's two approaches: add everything, what I wouldn't recommend, or you say everything that is higher than 0.01 watt per Kelvin or watt per meter Kelvin. Watt per Kelvin is a point, watt per meter Kelvin, meter linear thermal bridge. When these values are higher than 0.01, then we enter them into the PHBP, and everything else that is smaller, we forget. Even negative values. You could have a negative value with like minus 0.1. Yeah, so it's a significant thermal bridge, but from a thermal calculation perspective, this one has no impact. However, we still want to assess these ones from a temperature point of view. We want to make sure there is not a temperature in that thermal bridge that is so low that we have mold growth on it. That 12.6 degrees, that 80% relative humidity. Yeah, so that's two different things. One is our thermal modeling and seeing how much energy we need to deliver to the building, and the other one is the hygiene check, where we check is this thermal bridge actually causing a hygiene issue. Good. And then after we went through the thermal bridges, we said vapor control, so vapor barrier, vapor control, and we learned that we're not building 100% airtight. And because we're not building 100% airtight, the air is always moving moisture into the structure. And what we have to do with our vapor management, our vapor control, is that the structure has a higher drying capacity than absorption capacity. Yeah, so it has to be able to let more vapor out than vapor in. Yeah, and that's pretty much what the vapor management is standing for managing the vapor in our structure, making sure that the amount of moisture that is in there is able to get out again. So we need to let the moisture that gets in, we need to be able to let that out again. As well, it's the difference between the air tightness and weather tightness on one side, what is one layer. Yeah, the weather tightness is one layer, the air tightness is one layer. The vapor management is through the whole buildup. Yeah, so the ideal buildup is most vapor tight material on the warm side, and then less vapor tight, 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 until it's on the outside, so that the vapor always moves to the outside, always moves through the outside. That's from a simple building physics approach. That's what we try to achieve. This is obviously not always possible. And when we are now having a vapor resistance that is high, then a low, then a high, then we need to look, how is this vapor pressure in my structure? Is that a risk or is that not a risk? Yeah, and by changing the resistance of a membrane, or changing the resistance of a building material by replacing it with another building material, we can fix these things. And this is now this vapor management of our buildups that we can do. Good. So that was pretty much we've done on our first core day. Was that bringing it nicely together? Was that making it a bit more clear what we tried to do? Yeah, good. Then today we cover, like I said already, the most expensive part of the building envelope. The part where we have the most leaks on a water level, on an air level, even on a vapor level, where we're having a lot of thermal bridges, maybe not most thermal bridges, but plenty of thermal bridges on us and mold problems. And it's the most difficult part in the building envelope. So this makes this day probably the most important part of the course. So please stay focused, take notes, and mark your slides so that you can learn as much as possible of it. Can you do this? Yeah, perfect.